Welcome to Numbers Simplified. In this channel, we seek to simplify and solve numerical problems. We're still continuing with our financial mathematics series, and today we'll be looking at loan amortization, or the present value annuity. These two can be used interchangeably, of course. This is part 15, and take note. Loan amortization refers to the spreading of the cost of intangible assets or paying off a loan in equal installments over time. The payments cover both the interest and the principal, but early payments cover a larger portion of the interest. However, when we flip the sides, that is to say that the borrower becomes the annuitant, lending out an amount in order to get regular payments. It could be from a bank or an insurance company with interest on each outstanding balance. In this case, we have a present value annuity. So in this session, we will apply one approach, but the annuitant has to be identified in order for us to distinguish on whether we are dealing with an amortization or the present value annuity scenario. Now, the formula for the amortization is given in this manner. PV, which is the present value, is equal to PMT times the compounding period over the interest rate, multiplied by 1 minus 1 plus the rate over the compounding period raised to the power minus years times the compounding period. We are going to label this equation 1 for ease of reference. And take note, when we looked at the future value annuities, we had a 1 subtracted from 1 plus r over I term, and also that term was to the positive ni. So take note of the difference that takes place here. So that is the difference between the future annuity and the present value annuity. So PV represents the present value. PMT is equal to the amount that are going to be paid regularly. So these are the equal amounts that are going to be paid regularly. And R is the decimal interest per annum. N is the number of years. And I is the number of periods in a year. So in order for us to determine the PMT, given all the other variables, including the present value itself, from equation 1, we are going to multiply both sides by r over I. In so doing, we would clear the I over r term. So what we do on one side, we also do on the other side. Therefore, we are going to have the PV r over I is equal to PMT times 1 minus 1 plus r over I raised to the power minus ni. So of course, we are trying to make PMT the subject of the formula. So what happens next is to divide throughout by that whole chunk that is in the curved parenthesis, the bigger curved parenthesis or pair of brackets. So dividing by that, we are going to end up having PMT being equal to PV times r over I all over. So in the first set of parentheses, 1 minus, then in the second set of parentheses, 1 plus r over I raised to the power minus ni. That would be our PMT, or we can rewrite it in this particular manner. Now we are going to label this equation 2 for ease of reference as well. Right, so with these two formulae that we have right now, let us look at an example. Example 1. For a 20-year loan of $650,000 from a bank charging 11% interest per annum, compounded monthly What is the minimum monthly payment to be made to clear the loan? The solution. So as usual, it is crucial that we identify each and every variable that we are given. So the first thing that we note is we are given the number of years. So our N is 20. The value of the loan itself, that is at the present value, it's $650. Then the interest rate is 11%, that is to say 0.11. Then the compounding period is 12, since we have 12 months within a year. Then we are looking for the PMT. So what this means is we are going to apply formula 2. There's no need for us to derive it again since we have already derived it. So now from equation 2, we are going to have PMT is equal to that. So now the next thing would be to substitute for each and every variable. So starting with R, we have R in two places, 0.11 and 0.11. So in two places, we substitute for that. It is crucial that we make sure that we substitute the variables in the right position. Otherwise, our solution becomes wrong. Now, the next thing that we can go for is the compounding period. So we've got the compounding period in 3 places. So in 2 places is a denominator, and in 1 place is a power. So 1, 2, 3, we have it there. Then of course, we can go on to the present value, PV. This is 650,000. So we substitute that one. It's just there in 1 place. Then the last thing that remains is the number of years. There are 20 years, and this is in the power. So we substitute that, we have that. So we also have to make sure that we have substituted everything. That's one thing. Then the second thing, just be sure that we have substituted everything in the right place. Otherwise, all our work would be in vain. Right, so with that, the next thing would be to deal with what's within the pair of brackets or the set of parentheses first before we expand. That is important. Of course, I know some people can actually input these values in their calculator straight away. It's possible to get a correct answer, yes, but it's not advisable. Right, so simplifying what we have within the pair of brackets, we are going to have, so for the first set of brackets, we would have 11 over 1,200. So with this one here, you can express it as a fraction as I have done, or keep it as a decimal. But now, if you keep it as a decimal, make sure to keep it to either 4 or 5 decimal places so that you don't compromise on the accuracy of the answer. But where you can keep your answer exact, keep it exact. In that way, you would get an answer that is very close to the exact answer. So now, we would do the same thing for the inner pair of brackets in the denominator, so that we have 1 plus 11 over 1,200. And of course, the powers, when we multiply minus 20 times 12, we get minus 240. So we simplify further because we are going to make our lives easier and avoid also the possibility of making mistakes. Because if we just input the values from word go, we might make a lot of mistakes. And that's not what we're looking for here. We want something that is very accurate and precise. So now we move on to the inner bracket within the denominator. So combining 1 and the 11 over 1,200, we are going to get 1,211 over 1,200. So that's one way of simplifying that one. So going further, now we can no longer keep this one exact. That is the inner bracket in the denominator. So we are going to evaluate this, but as we evaluate it, we are going to keep our decimal places to either 4 or 5. So the more decimals you keep, the better. But of course, we do not want to have 10 decimal places. Otherwise, we wouldn't even have the space for that. So 4 or 5 decimal places is just sufficient. So simplifying that one, we are going to get 0.11192 in the denominator. And of course, subtracting what we have in the denominator, we are going to have 0.88808. That is when we subtract 1 minus 0.11192. Then, of course, we've got two fractions multiplying each other. And as we would know and recall, when we are multiplying fractions, we multiply the numerator with the numerator and the denominator with the denominator. But before we do that, we see that in the denominator of the first fraction, we've got two zeros, and we also have two zeros in the numerator of the other fraction. So meaning that we can actually clear the zeros so that we actually simplify our fractions to be 11 over 12 times 6,500 over 0.88808. Now, multiplying the numerator with the numerator, we are going to get 71,500. And the denominator with the denominator, that is to say 12 times 0.88808, we get 10.65696. So note, I have decided to keep the decimal places to 5 so that I don't compromise on the accuracy of my answer. And of course, this one here is easy to evaluate so that we get our answer as $6,709.23. And I hope that makes a lot of sense. In order to determine the number of payments or total periods, NI, given all other variables from Formula 1, which is the present value annuity formula or amortization formula. The formula is given to be that. Now, we see that we can actually divide throughout by PMT, which are the equal regular payments. So because we are trying to make NI be the subject of the formula. So that is the first thing that we do. So doing so, we are going to get PV divided by PMT on the left-hand side. And on the right-hand side, the PMT is gone because we divided PMT on both sides. So the next feasible thing to do would be to multiply by R over I, or simply dividing by I over R, which is the same as multiplying throughout by R over I. This would cancel out the R in the first set of brackets on the right-hand side and cancel out with the I as well. But at the same time, it would be relocated to the left-hand side. So when that happens, we are going to have PV over PMT times R over I, which is equal to 1 minus, in their set of brackets, 1 plus R over I raised to the power minus NI. Then, of course, we can interchange the position of the chunk that we have in the brackets that is on the right-hand side. We relocate it to the left-hand side. So as it crosses the equal sign, it becomes positive. Then we move the PV over PMT term to the right-hand side. That also becomes negative. So that at the end of the day, we have this expression over here. So one may ask, but why do we do that? Why do we really have to do that? I would prefer to have my unknowns, which I want to make the subject of the formula, on the left-hand side, and also dealing with the negative sign is another thing that I wanted to do. So that would be crucial and beneficial. However, if you decide to move the 1 to the left-hand side and solve, it will still give us the same answers. Now that we are here, the next thing that we are going to do, because we are trying to get something that is in the power, we are going to introduce the natural log. So natural logarithms, once we introduce a natural log on the left-hand side, we also have to do the same thing on the right-hand side. So this would affect everything that is within the right-hand side, or on the right hand side. Also, recall from the laws of natural logarithms, when we have the natural logarithm of x to the a, this would give us a times the natural logarithm of x. That is to say that we take the power to the left hand side and it multiplies with the natural logarithm of x. So applying the same concept, we are going to have the minus ni multiplying with the natural log of 1 plus r over I. So the right hand side remains the same because we didn't have a power there. Right then, we have that. So the next feasible thing to do is to divide throughout by the natural logarithm of 1 plus r over I, because this would help us get the ni. And also taking note of our ni, which is negative. So instead of just multiplying by the positive, we are going to multiply with the negative natural log of 1 plus r over I, so that we get our final answer, ni being minus. So we are having a fraction. So the numerator is the natural log of 1 minus PV divided by PMT times r over I. That is being divided by the natural log of 1 plus r over I. Let's label this equation 3. So now this is how we would find the number of payments or the total periods. We can also go on to divide by I so that we find the number of years. So that's one way also of finding the years it would take to clear the loan. Since we have our formula now, let us look at an example. For a loan of $650,000 from a bank charging 11% interest per annum compounded monthly. If monthly payments are to be made are $10,000, how long will it take to clear the loan? So as before, it is crucial in as much as we are dealing with a similar question that we dealt with in example 1. Our PV is going to be $650,000. Our R, which is the rate of interest, is 0.11 or 11%. Then this is being compounded monthly. So our I is 12 months. Then we're looking for the time it will take when we are given the PMT of 10,000. So from equation 3, we are going to substitute each and every variable that we have. And as before, we are going to make sure that each and every variable is in place. Right, so we have the PV. PV appears one time, and it happens to be in the numerator of the numerator. Right, so it appears once, so we have our 650,000 there in place. We also have our PMT, which is in the denominator of the numerator, so that appears once. We have our 10,000. We move on to our R. So we have R in two places, one in the numerator of the numerator and the second position in the numerator of the denominator. So we have 0.11 in two places, so we substitute it in the right place. Now we look for I. So our I here is 12. So let's forget about the I on the left hand side and focus on the I's on the right hand side. So we've got I's in two places. So the I is in the denominator of the numerator and in the denominator of the denominator. So we substitute our I-12 in both places. So with that, we see that we have actually substituted for each and every variable, and we have done so properly. So the next thing, of course, would be to simplify whatever we have within the pair of brackets or parentheses so that we avoid making unnecessary mistakes. So considering the first fraction that we have in the numerator, we've got 650,000 divided by 10,000. That can be easily simplified because the zeros will clear out. We've got 4 zeros in the denominator and 4 zeros in the numerator. That would give us a 65. that simplifies our work. And of course, in the second fraction, in the numerator, we have 0.11 divided by 12. That can be expressed as a fraction in this manner, 11 over 1,200. But you don't need to do that. You can just leave it as it was. Now, in the denominator, I decided to express that fraction as 11 over 1,200. So with that, then I know that I can combine the two fractions. Well, not the two fractions per se, but I have 65 times the 11 over 1,200 that multiplied by 65 would give me 715. So this is basically multiplying 65 times 11, giving us 715 over 1,200. Now in the denominator, I see that if I add 1 plus 11 over 1,200, I can express this as a decimal because I can do that or keep it as a fraction. But now if I express it as a decimal, I'd rather keep it to 5 or 6 decimal places. But of course, I would advise you to make sure that you keep it to minimum 4 decimal places. And yeah, well, 6 decimal places is fine, but there's no need to. So, but I'll just keep it at 6 decimal places because I don't want my answer to be too different from the answer that I'm supposed to get. Right, so with that, then we are going to have that. And of course, simplifying further what we have in the numerator, we are going to have, so 1 minus 715 over 1,200, that would give us the natural log of 485 over 1,200 divided by the same denominator we had in the previous step. Now, simplifying what we have in the numerator, we are going to get a negative 0.90593. So let's keep that to 5 decimal places. Then also when we evaluate the natural log of 1.009167, we are going to get 0.009125. Now, this is a fraction that is easy to evaluate. And of course, we see that we've got 2 negatives over here. So we know that a negative times a negative would give us a positive. So that would come out as positive. And dividing the values that we have, we are going to get an I of 99.28 months. So it would approximately take 100 months to clear this particular loan. And also, it is also important to note that we can express this in terms of years because we know that our I is 12. So substituting for the I, which is 12, so we are going to say 12n is equals to 99.28 and dividing throughout by 12 in order to get n. The n comes out as 8 years, and the 0.273 times 12 months, because that is just a decimal. But we know that in a year we have 12 months. So multiplying that with the 12 months, at the end, we are going to get 8 years and 4 months. So that will be the time it would take to clear the loan. So one other thing to take note of as well is the final payment after the 99 months won't necessarily be the $10,000 because take a look at this. We are paying for a period of 0.273 of the year. So meaning that the final balance would be given by the value of the loan after 100 months minus the future value payments up to the 99th month. So that difference there would give us the final payment that has to be made, and that payment should be less than $10,000. So that's how we would solve this particular question. Taking a look at example 3. For a loan with 12% interest per annum, compounded monthly, to be cleared over 4 years, how many payments will reduce the debt to less than half the original loan. So in finding our solution, we are going to use method 1, and method 1 would use the present value approach. There is also method 2 where we can use the future value approach, but for this specific example and moment, we are going to look at the present value approach. However, if you are interested in the future value approach, make sure to write in the comment section so that we work it out, and that will be interesting. Now, as before, let us identify each and every variable that is given to us. So firstly, we know that there is a loan that is given, and in the present value, let's call the value of the loan L. Since we are not given the loan, we are told also that it is meant to be cleared in 4 years' time. So our N is 4. Then the R, which is the interest rate per annum, is 0.12, that is to say 12%. And this is being compounded monthly. So our I is equal to 12. Right, so from equation 2 helps us to get the PMT, which is the equal installments that are to be made regularly. So PMT is given to be that. Now we are going to substitute. So we see that from our PMT, we've got 2 R's. So the first one is in the numerator of the first fraction, and the other one is in the numerator of the denominator in the second fraction. So we have substituted it in 2 places. Then we move on to the N. N is 4, and we only have one N, which is in the power in the denominator. Then we have the I, which is the compounding period. This is in 3 places. So in 2 places, it's in the denominator, and in 1 place in the power. So substituting for that, we would have it there. Then I'm sure we have substituted for every other thing. Oh yes, the PV. The PV is L, since we don't know the value of the loan. And of course, now the next thing would be to evaluate whatever we have that's within the pair of brackets. So in the first pair of brackets, we are going to have 1 over 100, because we know that 0.12 divided by 12, this is as good as saying 12 divided by 120. That would give us 1 over 100. Then we do the same thing in the denominator, in the fraction that we have there. So we have 1 plus 1 over 100. And of course, the power minus 4 times 12 would give us a minus 48. Right, so simplifying further, we are going to have the denominator in the denominator in the second fraction being 101 divided by 100. With that, we simplify that raised to the power minus 48, because there is no other way we can simplify this one further except to make it and evaluate it as a decimal. And if we do so, we have to make sure that we keep our values to either 4 or 5 decimal places. Now that would give us a 0.62026. So we've got 2 fractions here. And before we talk about the 2 fractions, let's evaluate the denominator in the second fraction. So 1 minus 0.6206, rather 0.6026. We are going to get 0.37974. Now we are going to multiply the numerator with the numerator, the denominator with the denominator, so that we get PMT of L over 37.974. Right, so that is going to be our PMT, or we express it in this manner. So that is the same as saying 1 divided by 37.974. That will give us a 0.0263 L. That will be the value of our PMT. Therefore, the value of the loan in NI periods or payments, since we don't know how long this would take, and that is what we are actually looking for, we are saying that the value of the loan in NI payments. So in order for us to get the value of the loan in NI payments, we are going to have it as L times 1 plus 0.12 divided by 12 raised to the power ni. And that is what would have given us the future value of the loan after ni payments. Now that from the previous step, we know that the 1 plus 0.12 divided by 12 would give us a 1.01 and raised to the power ni. So that would be the value of the loan after N1 payments, that is in the future state. Now, we know that the present value of the loan currently is L, so we would keep it to that. And also the present value of the NI payments to be made. So take note, the future payments of the loan were given by that step LV NI. But now we're saying that if we are going to make the payments, now we take it back into the present, we are going to have PVNI. And making use of the PV formula that we have in Formula 1, we are going to substitute for each and every variable that we have in that particular formula. So that would take us to have the PVNI of PMT times 12 divided by 0.12 times 1 minus 1 plus 0.12 divided by 12 raised to the power minus ni. Right, so with that then, we have substituted for each and every variable that we are given. And of course, evaluating what we have, we are going to substitute for the PMT because we have already obtained the PMT that we calculated earlier on. And that is the value that we have on the left-hand side of 0.0263L. We substitute it in place of PMT so that we have our present value NI. That is to say, the present value after NI payments is going to be 0.0263L times the 100 that we obtained when we divide 12 by 0.12 times what we have in the second set of parentheses. So that will be 1 minus 1.01 raised to the power ni. Now with that, we see that the 0.0263 multiplied by 100 would give us a 2.63L times the 1 minus 1.01 raised to the power minus ni. That would be our PVNI. So now that we have the present value payments, so that is to say that the value of the payments that are going to be made in NI periods in its expressed as the present value and the PMT that we have, we can actually get the present value balance of the loan, because remember, we have the value of the loan after the NI period. We have calculated that, and we also have the present value of the NI payments that we made, including the interest. That is what we are going to say the value of the loan right now, because we are talking with regards to the loan right now. So the value of the loan minus the PVNI payments value that we have calculated, and that should be less than half of the L. So now that particular L, we bring that L into the present value. So that's why we are having 1.01 raised to the power minus ni, because we want to get that present value of the loan in the present. So that loan is going to have a certain value in the future, but we're bringing back into the present. So we want to express everything in the present sense. So as you would know, the value of $100 now will not be the same value after 10 years. What we have is the value of the $100 right now, but after 10 years, that's going to be a different amount. So that is the same logic that we're using. We are keeping everything in the present tense. So whatever the value would be in the future, we are bringing it back so that we get the present value of the loan. So we are getting the present value of half the balance of the loan in the present, what it would be worth in the present. That's why we are using the to the power minus ni. Now, we are going to substitute for each and every variable once again. So we know that our PVNI was obtained to be 2.63L times 1 minus 1.01 raised to the power ni. So that is what we calculated. All the other terms remain the same. So now we can expand the first bracket on the left hand side. So when we expand it, we are going to have L minus 2.63L plus 2.63L 1.01 raised to the power ni. Take note, we were multiplying with the negative, so the first one becomes a negative and the second term becomes a positive. So that is what we would get. And of course, the next thing would be to group the like terms. We see that in the first two terms, these are L terms, and these can actually add up. So this is as good as saying 1 minus 2.63. That will give us a minus 1.63 L. The other term cannot be added because it has the power minus ni, which would complicate things. So let's keep it at what it is right now. So now we are going to move the terms with the power minus ni, which is the 2.63L times 1.01 to the power ni. Of course, the next step would be to divide throughout by L, since we have L in all three terms. So now when we divide throughout by L, we would end up having minus 1.63 plus 2.63 times 1.01 raised to the power ni, and that will be less than half of 1.01 to the power minus ni. Then of course the next thing would be to move all the terms with the power minus ni on one side. So I'm going to move the 2.63 times 1.01 raised to the power minus ni to the right hand side, so that we have a 0.5, because the 0.5 comes from the half. 0.5, 1.01 raised to the power minus ni minus 2.63 times 1.01 to the power minus ni. That would be that. And of course, as we group the like terms, we know that this is the same as saying 0.5 minus 2.63, since the terms are the same. That would give us a minus 1.63 on the left hand side is less than minus 2.13 times the 1.01 raised to the power minus ni term. And we are going to interchange the positions of these values so that we have a positive 2.13 times 1.01 raised to the power minus ni, because we want our unknown to be on the left hand side. Then the other term becomes positive 1.63. Now we divide throughout by 2.13. When we do so, we're going to have 1.01 raised to the power minus ni being less than 0.76525. And introducing the natural log on both sides, we are going to have that. And of course, recalling from the properties and the laws of natural logarithms, we know that we can actually express that as minus ni multiplying the natural log of 1.01 is less than the natural log of 0.76525. Now we have our ni, so we can divide both sides by the natural log of 1.01. And since the ni is negative, let's divide throughout by the negative as well, so that we have ni being greater. So now as we divide with the negative, we know from inequalities, if we divide or multiply with the negative, the sign changes. That is to say, the direction of the sign changes. Therefore, we are going to have the natural log of 0.76525 divided by the natural log of 1.01. And simplifying further, we are going to have ni is greater than 26.8. And take note, ni is the period of payments. So this is not the time, but the period. Therefore, this is 27 payments, approximately 27 payments, because we cannot make 26 payments. What happens to the 0.8 payment? So we are going to have it as at least 27 payments. That would clear the balance. And remember to subscribe so that you don't miss out on any of our future uploads. Make sure to check out all the other playlists we have so far. They might be beneficial to you, especially if you are a mathematics, statistics, financial mathematics student. And of course, I'll leave you with the following task. Find a question and post it on the related topic. Remember once again, your questions, feedback are always welcome here. Subscribe, like, and share so that you don't miss out on any of our future uploads. Thank you for watching Numbers Simplified. Remember, God loves you.